I am fascinated by how secure systems work, and the new Galileo satellite navigation system is no exception. One of its coolest features is called OSNMA, or Open Service Navigation Message Authentication. It allows you to verify that the GPS signals you're receiving are legitimate. So it can help prevent spoofing attacks. But what does spoofing actually mean? If someone spoofs a GPS signal, it means they've tricked your device into thinking it's coming from a real satellite when it isn't. Spoofing is different from jamming. Jamming is when someone interferes with a GPS signal so that it can't be used for navigation. Both spoofing and jamming are possible attacks against the Galileo system, but this video will focus on spoofing. OSNMA uses a cryptographic protocol called Tesla, which stands for Tracking Error and Spoofing Limitation with Algorithm. In this video, we'll deep dive into the technical aspects of how OSNMA works, including the cryptographic equations and concepts. So, if you prefer something more conceptual, check out my other video on how Galileo anti-spoofing works. Here we go. The OSNMA protocol consists of 7 steps. 1. A satellite creates a navigation message and then computes a MAC or message. Authentication code using a secret key K from a one-way hash chain. The hash function is denoted by H and then indicates the current epoch or update number. Epochs are typically updated every 30 days. 2. The satellite sends the MAC in the reserved NAV fields of the navigation message. And the key disclosure delay is set to D, where D represents the number of slots after which the key will be disclosed. The key disclosure delay varies between 7 and 24 hours. 3. After the key disclosure delay, the satellite discloses the key K in plain text. Now let's see how the receiver works. 4. The receiver authenticates the key via the Merkle route. This is done to ensure that the key hasn't been tampered with during transmission. 5. Using the received key K, the receiver recalculates the expected MAC and compares it to the received MAC. If they match, the receiver has successfully authenticated the message. Now, let's take a closer look at the cryptographic equation and the concept of Merkle routes. We have 2 equations. The first one describes how the key is generated based on the previous key kj, meaning each key is the hash of the previous key. This is called a hash chain. The second equation shows how the MAC, or message authentication code, is calculated using the data from the satellite navigation message and the current key K. The hash function, H, is truncated to an L-bit value to generate the MAC. When the receiver receives the signal, it knows the previous key kj and uses it to calculate the expected key K. If the received key matches the expected key, it proceeds to step 5. Then it uses the received key K to calculate the expected MAC if the received MAC matches the expected MAC. Then the message is considered authenticated. Let's talk about the time aspect. The time difference between the receiver and the satellite must be within plus minus 165 seconds of Galileo system time. Otherwise, the OSNMA algorithm will not be valid. The time required to achieve the first authenticated fix is called the TTFAF. Time to first authenticated fix. For Galileo, the expected TTFAF is around 60 to 120 seconds. It's important to note that OSNMA doesn't protect against jamming. Also, if the key is interrupted, the receiver won't be able to authenticate any messages until the next epoch. Finally, OSNMA is sensitive to synchronization issues. If the receiver loses synchronization with the satellite, it needs to wait until the next epoch to resynchronize. So, when should you use OSNMA? OSNMA is particularly useful in applications where the risk of spoofing is high, such as aviation, autonomous vehicles, telecom, and critical timing applications. In the future, Galileo will provide quantum safe chains to replace the current OSNMA implementation. They're also working on improving spoof detection using AI and other techniques. Moreover, Galileo second generation, or G2, is being developed to enhance the security and performance of Galileo. G2 will offer improved anti-jamming capabilities and a more precise signal. When Galileo G2 becomes operational, it's likely that OSNMA will be upgraded to leverage these new features. That was a lot of information, so here's a quick recap. OSNMA, or Open Service Navigation Message Authentication, is Galileo's system for verifying satellite signal authenticity. It's designed to prevent spoofing attacks, where fake signals trick a GNSS receiver into calculating a false position. OSNMA does this by using a cryptographic protocol called TESLA. Each satellite generates a unique key from a one-way hash chain. A message authentication code, or MAC, is created using that key and a hash function, then transmitted within the satellite's navigation message. After a short delay, the satellite reveals the key, allowing the receiver to verify that the message was authentic. The receiver calculates its own MAC using the same key and compares it to the one received. If they match, the message is trusted. OSNMA also uses Merkle hash trees to ensure key integrity. If the root matches, the entire key chain is valid. While OSNMA helps protect against spoofing, it does not prevent jamming, which blocks signal reception entirely. It also relies on accurate time sync. Losing it means messages can't be authenticated. Despite these limits, OSNMA is a major advance in GNSS security, especially for applications like aviation and autonomous systems. If you want to learn more about OSNMA, I'll provide some resources in the description below. Thanks for watching, and I hope you learned something new. If you liked the video, please consider subscribing, and I'll see you in the next one.